Hi, everyone. I'm delighted to be here, and thank you very much to the conference organizers for putting this together. It's great to have an in-person conference after all this time. Today, I'll be talking about a paper entitled Nature and Nurture. I'll keep track on time. Evidence from molecular genetic data in Korean-American adoptees. And this is joint work with Lauren Schmitz, as well as James Lee and Matt Mayhew. And I'm Jonathan Beauchamp, for those who don't know me, from George Mason University. Okay, so as you all know, the nature and nurture debate has a very long history. But interestingly, economists have been captivated by this also, at least some economists, for about the past few decades, maybe 50 years. And over that time, twin and adoption studies have established that both genetic and environmental factors matter for most traits, including economic traits. And however, limitations in the studies that were done over the past few decades made it difficult to quantify precisely the influence of nature, nurture, and the interaction. So for instance, twin and pedigree studies, when I say pedigree studies, I mean also looking at other family moments like uncle, aunt, cousins, and so on, and adoptions, they often rely on important identifying assumptions. And selective placement also limits inference from adoption studies. That is because the children, the adoptive families are often similar to the biological families of the children. So in a pioneering paper in 2007, Bruce Sacerdote studied adoptees who were quasi-randomly matched to adoptive families, which made causal inference about the family effects possible. And also a recent paper by Magne Mogstad and co-authors looks at this with Norwegian Korean adoptees, and he looks at the effects of family background on wealth. And that was in Journal of Political Economy just out this year. So now technological advance also makes it possible to work directly with molecular genetic data. So in this paper here, we combine these two innovations, if you want. We have quasi-randomly allocated adoptees, as well as molecular genetic data. So we basically have quasi-random allocation of genetic data to adoptive families. Okay. And okay. So here's the overview of results. I should have said also we work with Korean adoptees, as the title says it, because that's what gives us this quasi-random assignment, as I'll discuss a bit later. Okay. So using standard behavioral genetic methodology, we find evidence. And using molecular genetic data and a suite of family variables, we find direct causal evidence that both genes, which means nature, and the family environment, meaning nurture, matter for a suite of outcomes. Okay, nothing new here. The only novelty here is we look at directly in regressions where we observe the variables in a setting where we have quasi-random assignments. Also, we find that family environment appears particularly important for educational attainment, which I'll often call just EA, that's years of education, income, drinking, and smoking behavior, while genes have particularly strong influence on cognitive performance and height, among other outcomes we study. On the whole, one thing we learned from this paper is that currently available molecular genetic variables, meaning the PGS, I've not used the term PGS yet because I haven't introduced it, but at this point in the conference, I think we all know what polygenic scores are. So those polygenic scores predict about as much as the family variables in our sample of Korean adoptees, despite the fact that those PGS are based on summary statistics from European ancestry GWAS, but I'll say more about that. We also find suggestive, but surprisingly robust evidence that genes for educational attainment and family SES are substitutes in the human capital production function for cognitive skills. So that's a G by E effect. Now, after Titus' presentation and others, we'll be skeptical of this result. I'll still present it. It's quite robust and stubborn, but we have a small sample size, so take it with a grain of salt. So statistical power is limited, and we'll need a replication of that. Okay, I'll skip this slide here in the interest of time. So for the rest of the presentation, I'll first describe the data we're working with. Then I'll talk about our investigation of nature versus nurture using old-style behavioral genetics methodology with the ACE model, which compared the resemblance of adoptive siblings to that of biological siblings. Then I'll talk about nature versus nurture, where we look into this with molecular genetic data and polygenic scores, as well as family variables. And then finally, we'll look at G by E, or nature and nurture interactions. So let's start with the data. So the data comes from the Minnesota Center for Twin and Family Research, or MCTFR. And we look in particular at 409 adoptive and 208 non-adoptive families, and they all consist of pairs of siblings. So the sampling of the data set focused on families that had two parents at the time of recruitment, as well as at least two kids. Some have more. And there's 428 of these kids are Korean adoptees, including 367 who have been genotyped. There's also 141 white adoptees and 471 white non-adoptees. I call them white non-adoptees. That means just biological kids that are still with their parents, and then their white adoptive parents. These are Minnesota families, so they're virtually all white in the sample at the time, the way it was sampled. And in this study, in this presentation today, I'll focus really on the Korean adoptees. I'll make some comments on the others. In the paper, we look a bit at the others as well, but in the interest of time here, these are the most interesting because they have this quasi-random assignment that I'll discuss more. The data were collected in 4 waves. When the adoptees were 15 years old on average, with a range of 10 to 21 years old. And then second wave, the mean age was 18, and then 22 for the third wave, and 32 for the fourth wave, which just became available this year, actually. And interestingly, the placement of the Korean adoptees in the adoptive family was effectively random. So that's by virtue of the fact that the way this was done, when you look at adoption in typical adoption, typical samples, social workers and adoption agencies try to place the adoptees in families that more or less resemble their biological families. Now, that's really imperfect. They're not exact matches, but still, there's some selective placement. Now, with these Korean adoptees, the way it worked is the parents applied to the adoption agencies to apply an adoptee, and they had very little say or knowledge of what the characteristics of the adoptee or his or her biological family was. So basically, it was just a matching process where the next parents in the pile were matched the next adoptee that became available. And we will test this formally on the next slides, and we find no significant association between the predetermined adoptive variables and the family variables. So here's that slide that tests formally for random placement of the Korean adoptees. So what we have here is 9 regressions with the dependent variables being adoptees' predetermined variables. So we have the adoptees' sex here, placement age. Placement age is just the age at which the adoptee was placed between 0 and 24 months. They were all placed before 2 years old. And then we have a bunch of polygenic scores for various traits. And we regress each of these on a kitchen sink of family variables here. So we have, font is a bit small. So we have father's years of education, mother's years of education, mother's height, BMI, log family income, a bunch of other things here, whether they're still married, the parents at the time of the last wave, whether they live in city and suburbs, and so on. All this to say here, the last line here is the F statistic for the full F test of all the coefficients in this regression, and we reject we fail to reject the null of the fact that the coefficients are jointly significant in all cases except for the first one here, where the dependent variable is male. So we cannot reject it. So it's possible there's been selective placement on sex of the adoptee, but then again, there's 9 regressions here, so we'd expect one to be significant by chance. Also, in all of this table, there's 108 coefficients, and only 4 of them are significant at the 5% level, so less than 5% are. So on the whole, not too much evidence of selective placement. Now, you might think, well, those PGSs, they might not explain that much. I'll talk a bit more about this later, but in the Korean adoptees. But so we replicated this analysis in the much smaller sample of white adoptees. So that sample is about a third of the size of this. And there we find huge evidence of selective placement, including for sex and placement age. So basically, that's comforting, the fact that we don't find any evidence of selective placement here except for sex, which we control for, but that for the whites, we find huge evidence of selective placement in a much smaller sample. Okay, so we'll focus on a suite of 10 adoptee outcomes, which include educational attainment or years of education, a college degree dummy, grade point average, soft skills, which is some measure of non-cognitive skills, cognitive performance or IQ score, income, a number of alcoholic drinks per week, whether one ever smokes, ever use nicotine rather, BMI, and height. And then the main explanatory variables are the polygenic scores that predict each outcome, and more on that below, as well as the family variables, which we saw on the previous slide. There's also a measure of SES we use. It's based on parental income, education, and occupations. and the baseline set of controls. Through all analysis, we control for some baseline set of controls, which include sex, age at which the trait was measured, the placement age of the adoptees, which is between 0 and 24 months, birth year, and for the analysis with the polygenic score, we also control for the 10 principal components of the genetic data, as is usual. Okay. All right, so now let's first look at the evidence from the behavioral genetic ACE model with the pedigree data. So this will be familiar with most people in this room, but I'll still go through it relatively rapidly because it will not be familiar probably for some. So the ACE model or AC model is the workhorse model in behavioral genetics. It's based on strong structural assumptions, as you'll see very soon, but decomposes the variants of trait Y into shares due to genes or additive genetic factor A, family environment C, and the rest E. And so Y is equal A plus C plus E, or genes plus family environment and the rest. And then it assumes that A, C, and E are independent. That's a very strong assumption, of course. However, in Korean adoptees, it makes sense because the adoptees were quasi-randomly assigned to their families. So there's no reason to assume except to the extent that the environment reacts to the genes, of course. Then from genetics, we know covariance in the additive genetic factor is equal to half sigma A squared for full SIBs, but 0, of course, for unrelated people. And then the covariance in the family, the C term, the common family environment, is equal to sigma C squared for any two kids raised in the same family. Okay, anyways, putting all this together, we get the covariance between the outcomes for biological siblings equal to half sigma A squared, plus sigma C squared. And for the adoptees equal to sigma C squared. So basically, we'll see the estimates on the next slide. Just keep in mind, basically, the sigma C squared here is just a correlation between the adoptive siblings, okay? And for this, we only use adoptive sibling pairs for which one of the sibling was a Korean adoptees. So there's really no selective placement here that will affect the estimates because the only relation you have between the two adoptees in the pairs we study are the family environment because at least one adoptee was quasi-randomly placed in that family. And for the biological kids, we just use the white kids that are biological, that are still with their parents, okay? And so basically what we'll do basically in the next slide is just compare the adoptive sibling correlation, which is the index of how much the family environment matters, to that of the biological sibling correlation, which is the same sigma C squared plus a component here that reflects the influence of genetics. Okay, so here are the results. In panel A here, we have the adoptive and biological sibling correlation, while in panel B, we have the decomposition into the sigma A squared, sigma C squared, sigma E squared. So let's first focus here on educational attainment. What we see here is that the adoptive siblings have an educational attainment that's correlated at 0.22. Well, so that's strong evidence that family environment does matter for educational attainment, consistent with what's, with the literature. So nothing too surprising here, but it's nice to see this with quasi-randomly placed adoptees. And also the sigma C squared term is exactly the same here. So generally speaking, here we find evidence of family environment for college, educational attainment, soft skills, income, and smoking, and drinking also to some extent. While genes seem particularly important, if we look at the difference between biological and adoptive sibling and translate this into sigma A squared, they seem particularly important for cognitive skills, height, and BMI. Okay, so anyways, that's consistent with the literature, nothing too surprising here. And Bruce Sesserdote also did very similar analysis with a smaller set of outcomes, but still, so nothing too surprising so far. Now, we will look directly with molecular genetic data at this. Okay, so first I'll have to define polygenic score. I don't have to define it very much here because it's already been done by previous presenters. All I'll say is that we construct our polygenic score using PRSCS, which is a software similar to LDPRED, basically. It's a software that slightly better than just taking the weighted sum of the SNPs. It also adjusts for the correlation between the SNPs, adjusts those beta coefficients for the correlation between the SNPs. We use GWAS from individuals of European ancestry to predict, to construct polygenic score and predict in Korean ancestry individuals. And as you probably have heard, many of you, transethnic portability of polygenic score is often quite limited. But thankfully, as you'll see on the next slide, it's not too bad. We still predict quite some variation in the traits we care about in the Koreans. And one advantage of doing this, however, is that population stratification bias is likely to be less of an issue than when you predict in Europeans. Okay. All right, here are the incremental R-squared of Poljnik score. I'll define what I mean by this in a second, but basically here you have 10 different outcomes that we care about. And for each outcome, you have a bar, a pink bar for the white parents, a turquoise bar for the white non-adoptees, and a green one for the Korean adoptees. And so what we're showing here, for instance, for cognitive performance, on the y-axis is the incremental R-squared. Let's say let's focus on the pink bar here. It gives the difference in R-squared from a regression of cognitive performance on the Poljnik score of cognitive performance and the baseline controls, and the same regression, but without the Poljnik score of cognitive performance. Okay. So here we see that the cognitive score of cognitive performance predicts about 8% of the variation in cognitive performance in the whites and almost 5% in the Koreans. Also, a Poljnik score of educational attainment explains almost 5%, a bit more than 4% rather, of college, and more than about 6% for educational attainment, and so on. So, and for height, we predict almost 7%, and so on. So the bottom line of the slide is here, the Poljnik scores do predict less in Koreans than they would in whites, as you'd expect, and as many studies have shown, this is what you'd expect. Of course, it doesn't mean anything about the mean, it's just about prediction of the variation. But they still predict, so we can go forward and use these scores and do some analysis. I should also mention the scores predict very little for drink per week here, actually, and in fact, we get the wrong coefficients. Actually, I should have done this for this presentation, but in further analysis, I'll just delete that score for the Koreans because it makes no sense. It's pretty much noise. Okay, so we'll do several exercises here. The first thing we'll do is we will regress children outcomes on family variables. Stepping back, just some background here. So regressing children outcomes on family variables may yield bias estimates of the effect of family variables. This is well appreciated. We know this. Family variables may be correlated to children genes. You can't just go around and regress children variables and parents variables in typical sample. And even in adoption studies because of selective placement. But here we can do this because we have quasi-random allocation of the adoptees to the families. So basically, the family variables, we can really, you can really interpret the regression coefficient, not necessarily as causal, because it could be, it could be capturing some correlated variables, but at least as unbiased. Okay. But similarly, also, as has become more appreciated over the last few years, only regressing children outcome and children PGS may also yield bias estimate of the effect of PGS. And this, that's the famous phenomenon of genetic nurture in particular, where children PGS are correlated with parental genes and thus family environment. But here, because we have this quasi-random assignment of the Korean adoptees, we get unbiased estimate of both family variable and PGS. However, to be fully thorough here, the effect of PGS of the children, the effect of children PGS may still capture the effects of in utero and pre-adoption environment for the Koreans, right? Because they may be correlated with this. The quasi-random assignment just occurs after at adoption, basically. Okay, so we'll do two exercises here. The first one is that we'll regress the adoptee outcome, each adoptee outcome on the whole set of family variables and the adoptee PGS and the baseline controls. Again, the family variables, I won't read them again for you, but there's a whole set here that are listed and that I've shown before. And for the adoptee PGS, we'll regress all 7 Poljnik scores. Okay, and here are results. In the paper, we show the results variable by variable, but that wouldn't fit in the slide. So here, all I did is I show for each of the 10 outcomes, I show the incremental R-squared of each block of variables. So let's focus here on educational attainment as an outcome. This number here is the incremental R-squared of adding adoptive family variables in a regression of educational attainment on the baseline control. So basically, we regress educational attainment on the baseline control, and then we regress this again, but add the block of adoptive family variables, and then the R-squared increased by 14%. And similarly, when we add to the baseline control the adoptee genetic variables, it increases the R-squared by 7.7%, percentage point rather. Okay, so what's the takeaway from this slide? Well, first, for educational attainment, well, both genes and family environment matter. that's not that surprising, but it's quite incredible that we can explain 40% of the variance in education attainment with the family environmental variable that we observe. So in behavioral genetics, always been a bit of a puzzle. What explains the C-squared? This latent variable is unobservable. So it's quite nice here that we can explain that much. And actually, for education attainment here, what matters a lot is log income of the parents as well as mother's education. Okay. For college here, strangely, it's not significant. That's more of a quirk, I think, simply because when you have so many variables and some don't matter that much, the F-test might fail to reject. And also, we use the Nagal-Kerr square here because it's college. It's a binary variable. But on the whole, we find influence of family environment variable on pretty much all the traits, and also for the polygenic score on pretty much all the traits. Again, for BMI, surprisingly, it's not, even though the score of BMI alone is significant. That's, I think, just a quirk of the F-test when you have 6 other scores that might not be relevant. So, I mean, surprise, surprise, both family environment and genetic variables matter, but it's nice to see it directly when we use the actual variables in regression as opposed to just behavioral genetics decomposition. And when we have quasi-random assignment where we can really estimate, interpret these as unbiased. Okay, we do a second exercise in the spirit of Cesar-Daoud's paper, where we define 3 types of family. So the first type is type 1, where we'll call them the high education small families. So these are families where both parents have 4-year college degrees, and they have 2 or fewer children, or they're in the top SES, top 20% of SES distribution. Then type 3 family are families where neither parent has a 4-year degree, and they have 3 or more children. So these are the low education large family, or their SES is in the bottom 20%. And then type 2 is simply none of these. So then we also compare these results with when we define 3 terciles of each polygenic scores. And then for each adoptee outcome, basically we regress the outcome on a type 1 dummy and a type 2 dummy to see the treatment effect of being assigned to a type 1 family relative to being assigned to a type 3 family, which is the omitted variable here. And these treatment effect here can be estimated, interpreted as really causal because of the quasi-random assignment. Yeah. Then we compare this to the treatment effect of having a tercile 3 score versus a tercile 2 score, okay, which can also be interpreted as causal, again, because of this random assignment of the adoptees. Okay, so here are the results. In the first panel, we show the results for regression on the family treatment effects, or the family type dummies, I'm sorry. And what we see here, and the second panel is for the PGS, but let's focus on the first panel here. So what we see here is that for educational attainment, being in a type 1 family increases your years of education by 1.369 years, and it's highly significant. So that's strong causal evidence for that. It also has an effect on cognitive performance, and college doesn't have much of an effect on the rest. Doesn't mean, this doesn't show there's no effect. It's just that we have a small sample size and we cannot detect it. But what's interesting there is when you compare these effects to those of the terciles of polygenic scores, those terciles are very significant as well. So, I mean, stepping back and just looking at these 2 exercises and the results, even though we have polygenic scores that are still quite noisy in the early days of GWAS, well, I don't know if we're still in the early days, but certainly not in the final days of GWASs. And even though we predict with European ancestry GWAS summary statistics in Europeans, those PGSs are predicting almost as much as those family variables. Now, it could be, of course, that we don't observe the right family variables, and that there's a secret family variables that matters much more, but still, it's kind of interesting to see this comparison here. Okay, now the final section, I'll talk about interactions between nature and nurture, or G by E, gene and environment. So there's lots of interest, of course, in understanding genes and environment and how they interact, because this can help us understand the human capital production function, intergenerational mobility, and may also yield knowledge of the differential effect of policies as a function of individual genotypes, which may in turn lead to targeted or personalized policy interventions in some future world you could imagine, with proper ethical guidelines, of course, and provide the right environment. So we could imagine targeted policy intervention that provide the right or optimal environment to help individual reach their full potential. However, the existing gene-environment interaction studies literature has been quite limited, except now it's improving rapidly now, thankfully. But here, what we think are 5 main limitations, The first one is that genetic variants typically have small effect size. So actually, I probably need to update that point here because now we have polygenic scores, and that's not an issue anymore. But traditionally, until recently, people were using single variants. Second one, which is still often an issue because it's very difficult to get at that, is that the environmental variation is not exogenous. So when you detect a gene-environment interaction, it could be really hiding a gene-by-gene interaction because the environmental variables correlate with the genes and so on. So ideally, you want to have environmental variation that's exogenous. Often also there's an inadequate specification for control variables. I'll talk more about this next slide. And no checks to see if the results are driven by scale effects, which I'll talk about in a few slides. And then finally, insufficient statistical power. So here, I'll claim that we addressed all four of the first points. And the fifth one, well, we're stuck with small samples. At least we do power calculations. Those power calculations are not that reassuring, but we do our best to address it, to think about this. Okay. All right. So we regress each adoptee outcome on family socioeconomic status as an omnibus measure of family environment, and the outcome relevant polygenic score and their interactions and controls. So that's specification we've seen before today. So outcome on socioeconomic status, polygenic score, and the interaction. And these here are the the suggestion of Matthew Keller, a behavioral geneticist, to control not only for the control variables, but also the controls interacted with the two interacting variables, in this case, SES and polygenic scores. When you don't do this, the interaction effect could be, there could be an omitted variable that drives the result for the interaction. So we do this proper control procedure here. And there's a gene environment interaction when the coefficient beta 3 is not equal to 0. When beta 3 is greater than 0, in technical jargon, economic jargon, you see the polygenic score in SES or technical complements in human capital production function of Y. When beta 3 is less than 0, then they're technical substitutes. Okay. And I'll skip the interpretation here. I think, we can interpret, well, I'll just say basically the way you interpret this interaction term is could be that SES modifies the effect of the PGS or that the PGS modifies the effect of the SES. You can't really distinguish between these two. Okay, here are the results. I'm just showing the results here for 6 of the outcomes. There's 2 here for cognitive performance. I'll talk about this in a second. I've cut the other results for smoking and all this simply because it didn't fit in the slide and won't have very tiny font. But the bottom line, for those other outcomes, there's nothing going on. There's no interaction, including for drinks per week and smoking. And reassuringly, no interaction either between gene and environment for height, which is kind of reassuring. Okay, so overall here in the first panel, we show the results without the interacted controls. What I mean by the interacted control, I mean this beta 5 and that should be beta 6 term here, without these 2 things. And then in model 2, we include the interacted controls. And we show the results here linearly for the polygenic score, family SES, and the interaction. We don't show just the effect of the PGS and family SES in the model 2 here because when you use interactive controls, these terms are not interpretable anymore. Okay, so we basically find no interaction except, interestingly, on cognitive performance. And so basically, what we do find here is a negative interaction between the score of cognitive performance, significant at 10% level only, and family SES. But that interaction is very significant if instead of the score of cognitive performance, you use the score of EA. Now you might wonder, why use the score of educational attainment? Well, because it actually predicts more of cognitive performance than the score of cognitive performance. And we had done the analysis using only that. And then we got the score of cognitive performance, and unfortunately, it's not significant. But anyway, since I'm pretty critical, I'm pretty skeptical of this result, I don't feel too bad presenting it this way with the score of EA as well. And when you do the control following Keller, it's still very significant negative interaction. So what does that mean in practice? If you were to take that result at face value, which, I'll remind you to take this with a grain of salt a few times, but suppose you take this at face value. Well, here's a plot summarizing essentially what's going on. So here we have 2 quadrants of, okay, 2 quadrants of the, on this axis here, 4 quadrants. In this axis here, we split the sample of Koreans for those who have polygenic score that's greater than the median and those that are less than the median. While here we have those who have family SES less than the median and those who have family SES more than the median. And what we see here is a saturating effect of, so basically children who have either a high polygenic score or high family SES seem to be doing well. So in these three bars here. But if you lack both, if you lack family SES and if you lack high family SES, and you lack a high Beauchamp score, then you suffer in terms of your cognitive performance. Okay. And if this result were robust and replicates in separate sample, well, that would be quite important for intergenerational mobility and so on. It would strongly, point towards policies to really provide a good environment for kids who have rather lower EAPGS. Okay. And also, this result is quite robust. So here are many robustness checks. So this is the base. So these robustness checks are all with the Keller interactive controls. Okay. And I did panel 1 here shows the results with the Beauchamp score of the robustness check with the Beauchamp score of cognitive performance. And here they are with the Beauchamp score of educational attainment. And these are more significant, but it's essentially the same story. So here's the baseline estimates. Then when we do it in males only and females only, it's not significant in females only, but it's a small sample, so you'd expect it to lose significance. It remains negative. When you split by age, it's still significant, even though the sample gets very small, despite all the controls we have there, and the degrees of freedom we're eating up. And this is the scale effect I was talking about. The scale effect is the idea that cognitive performance has no natural scale. So if you just square cognitive performance, then, our G/E results could just be driven by the fact that we have the wrong scale for cognitive performance or for by SES. So I won't go in detail here if it doesn't make sense to you yet. I'm happy to talk more after. But all this to say, we see what happens if we square cognitive performance or take the square root of it, if we square family SES or take the square root of it, and then when we use a really extensive set of controls that include basically the whole set of the family variables. And the results are pretty robust throughout. The only thing where they lose significance when we have the Beauchamp score of educational attainment is when we do it female only, but remains negative. Okay, so what to do with this? Well, should still take this with a grain of salt, because we did some power calculation and we derived an analytical expression to calculate statistical power under simple assumptions. And we have only 361 genotype adoptee in the sample for this. And so basically, in the adoptees, G/E are uncorrelated. So power is mainly a function of the unknown R squared of the G/E interaction and number of degrees of freedom. And we derived the analytical expression and verified this through simulation. The conclusion is that the statistical power to estimate a significant G/E estimate here in our sample of 361 Korean adoptees may be limited. I say may be limited. It really depends what you assume is the true R squared of the G/E interaction. So if you assume that the true R squared is 1%, then power is about 43%. If you assume that the true R squared of this interaction is 0.005%, then power would be 24%. But if you assume that the true R squared is 2.5%, the true R squared for the interaction, then power would be sufficient. Well, usually you call 80% power to be sufficient, whatever that means. But okay, well, how plausible is this? Well, by comparison, the R squared of Beauchamp score of educational attainment for cognitive performance, the sample of Korean adoptees, is 5%, and the R squared of the SES variable is 2%. So, is it plausible that the interaction is 2.5% R squared? It's not implausible, but I think it's a bit of a stretch, but, So anyways, take these results with a grain of salt. Okay, finally, to conclude, we analyze a unique data set of genotype adoptees who were quasi-randomly matched to adoptive families. And we do analysis with pedigree data, meaning the ACE model, and molecular genetic data. And these both indicate a role for genetic and family environmental factors. And the family environment is particularly important for educational related outcomes, as well as income, drinking, and smoking behavior. Genes are particularly important for cognitive performance and height. And there's a possible interaction effect between genes for educational attainment and family SES, but power is limited. So this may be a false positive, replication, more data as needed. And the implications of this, well, first, this provides insight into the human capital production function. It's good to open the black box of this and see, what's under this sigma C squared, and to study it in a setting where you really have quasi-random assignment, where you can really interpret the regressions of the outcomes on the scores and also on the family variables as being unbiased. Okay. Also, it's important to understand, the underlying sources of inequality and also the underlying variables that drive it, because people's views of inequality in surveys, as has been amply demonstrated, depend on the relative importance of the factors that contribute to it. Okay. And finally, our results, even though, we could not, it's very likely we don't have the right family variables exactly, and there's other family variables that matter. And of course, the project scores are noisy, and we predict invariance. Well, despite this limitation, at least these results are informative about the relative importance of variables that are currently available to researchers. It's quite striking that the scores, the project scores in Koreans are already doing quite well on a whole set of across the 10 outcomes in general, relative to available family environment variables. Okay. Thank you.
Yeah, I noticed that results for GPA looked a bit different compared to other phenotypes studies. For example, I think the family environment wasn't very predictive of GPA, but the genetics was strongly predictive. And GPA of children didn't differ very much between type 1 and type 2 families, but when you study by families based on PGS, I think it was very significant. I wonder if you can comment on this, and if this tells us anything about the difference between quantity of education and say student performance.
Yeah, well, the GPA, so the family variables they're not significant here in the joint F test for GPA. Let's see what it was for for here. We find, yeah. So in general, yeah. So what you're saying is, in general, the family environment seems relatively less important for GPA relative to just years of education or college. Is that your statement?
Yeah, but genetics is strong.
Yeah. So GPA, my interpretation of this is simply GPA captures in part some skills measure. It loads partly in cognitive performance. And, there is in fact the family environment of cognitive performance, as we can observe in the treatment effect thing here. But, cognitive performance has a huge genetic component as well. So I think that would be my guess of what's going on here. The GPA is highly loaded on cognitive performance as well. Not only, but yeah. Yeah, Kevin?
Yeah, I have a big question. Because I think it's fairly convincing that there's random assignment at the level of the adoptees to different families. But there is a kind of assumption that's made in terms of thinking about the policy implications of these effects, that variation in the measurements of SES here would map into the kinds of things that could be targeted by policy. And one possible just issue with interpretation would be, whether there's selection in terms of the low or high SES families into being adoptive parents. And if one was worried that the low SES families positively selected, that particular, I was wondering, is there any way to check how, at least on observables, how different these families, low SES families here are to low SES families? And
something like that. Yeah, it's a very good question. So there is a paper, and we discussed this in the paper, but there's another paper that looks at this, comparing the Minnesota twin adoption, or Minnesota study to census data for similar families. And yeah, they're definitely range restriction, basically, in behavioral genetics balance, meaning the families that adopt, very low socioeconomic status families cannot adopt. They're ruled out by adoption agencies. And also in the sample, there's not billionaires or millionaires either. So there's range restriction. I think in the paper by Matt McGew comparing that to census, as I said, I think he finds that, for instance, the variance for parents, I forget which variable, if it's educational attainment, Roland, do you remember?
Yeah.
Anyways, it's roughly, for a bunch of parents variable, he finds roughly 65% of the variance in the sample relative to census for comparable families. But again, I think he just compares them to families that have two parents together also. So again, you have huge range. So when you compare the set of families we have here to typical families with two parents together, you lose maybe 30-40% variance. If you were to compare it to all families in the U.S., that would be huge because, and he compares it to families in Minnesota, of course, not a whole. But if you compare it to all families in the U.S., of all groups, and also single parents family, then of course we don't. So yeah, that's a very good point. So these family treatment effects, as well as these family variable effects, and all these family effects we find are likely to be much smaller than what you find in the full cross sections of U.S. families. So yeah, that's a very good point. In another way, if you talk to many behavioral geneticists, they typically think, they often see family environment as having almost zero effect on many traits. And that's partly because they study psychological construct like cognitive performance, also height, psychological construct, and so on, that indeed seem to have a relatively larger genetic component. But for economists, if you look at educational attainment, despite this range restriction, we find quite some significant family influence, despite this range restriction.
I can show you some graphs now. So this paper addresses an important question, has a go at saying about something about an old and possibly important debate, which is what is the role of genes and family environments in determining certain outcomes that we think are important. So to address these questions, they use, as we saw, molecular data from children, adoptive and non-adoptive children, and their parents, which is an important issue, as we saw today already. They use a number of well-established PGSs and a rich array of variables. They start from the ACE model, which makes us recognize very strong assumption about the correlation between the A, the C, and E. And then they look at a number of more sophisticated models, as we saw, and they consider a number of different interactions. Throughout the paper, they use the differences between in different points of the paper, the difference between correlation between biological and non-biological siblings to disentangle the role of family environment. And they stress very strongly the importance of the quasi-random allocation of children to family. The findings, as we saw, that both genes and environment matter. The relative importance of these two factors changes across different outcomes. And the standard errors are all often very high, so that should be taken with some cautions. So what I'll do in my comments, I'll start with some really cheap shots, and I apologize for that. But it's not that I'm particularly keen on that, but I think it's useful to keep in mind some basic facts that we should all know and not forget. And then and by the way, some of these issues were mentioned both in the paper and in the presentation. And then I move on to some serious comments. Let's start with the cheap shots. This was just discussed now. How representative this sample of, do we care about, how interested are we in the population of families that adopt Korean children? Another slightly more nuanced point, but still pretty cheap, is there really what is really the difference between the biological and adopted children? And is this difference particularly useful? Is the assumption that the adopted children have the same family environment as the biological children correct? And by family environment, I guess it's not just what happens in the home, which is still an interesting question, but also what happens in schools, in the neighborhood, and the like. And finally, the things that I found, it is a simple point. I'm not sure why we want to start from the ACE model. And the paper goes past that. But I think the assumption that A and C are uncorrelated is, as was mentioned, is a really strong one. Now let's move to some more serious issues. I think the correlations they show in the paper are very interesting. And that's a comment that applies to several of these papers presented at this conference. The big issue is that once we know, and they're useful. I definitely do not want to sound dismissive here, but the big question is, how do we interpret these correlations? And so, what is the influence of gene that we see reflected in this correlation, and is that something more or less deterministic or not? I guess we all agree it's not. But then, what are we capturing, and how do we use these results? And the same comment applies to the environmental variation. And so, can we establish causal links between the variables that we observe on the left-hand side of our equations and the outcomes we're interested in? And I think the correlations, as I said, are important and useful, but without a model to interpret these results, it's not going to work. And granted, the inferences we'll make will depend on the plausibility of the model and of the identifying assumptions that we impose through the model on the data. But by all means, we should be very transparent about that set of assumptions. But in the end, it's needed. In my view, that's the way we advance knowledge. Let's think, for instance, about the family environment. The authors claim that the quasi-random allocation of adoptees to family solves some problems, and it really does. And they show table 2, the big table that was shown as a first piece of evidence, presents convincing evidence that the allocation of these Korean adoptees to families is uncorrelated with a number of baseline family characteristics. Now, does this solve the problem in terms of the equations we are trying to estimate? This is the equation they run. This is the family, this is the BGS, and this is the interaction between the two. The fact that the PGS is uncorrelated with the FI, it doesn't necessarily solve the possible endogeneity of FI. What we really care about is the correlation FI of epsilon I. It is useful to know that the PGS is uncorrelated with FI for a number of reasons. But if we care about identifying the causal impact of family environment on YI, then we care about the correlation of FI and epsilon I. And it could be that we are omitting some factors that are correlated both with the baseline. So they focus on the baseline stuff. But parental investment might react in certain ways to a number of shocks that we don't observe. And that if we introduce a bias here, then the whole inference becomes quite problematic. So the fact that FI is uncorrelated with PGS does not make it exogenous. Some observed parental investment can react to child development and to the PGS. What is needed is a clarification of what FI is. And this is a point that I was trying to make earlier in conversations over lunch. I think what we need as a next step to this research, we need to have a model of an interpretation of the production function of human development, recognize that it's addressed by that is affected by genes and by parental investment and by peers and the like, and then write down models for parental investment, which implies to say something about what parents do and what are the drivers of that. So parents make decisions about parental impairments, and these decisions may be in reaction to a variety of factors. One thing that I want to stress here and show you the pictures that I promised you, is some distribution of factors within the households might be very important. So the distribution of factors within the households might be important. And as I said, this is an issue that I think is really key, and it would be a key for this paper, but also for the previous paper that I was discussing. I think parents, especially parents in disadvantaged situations, often face very difficult choices in terms of distribution of resources across families. Again, this is probably not the sample that we looked at today, but this is a sequence of pictures that I took from a paper by Michele Gianola. It was a student at market last year, so I'm not trying to sell anything here, but this is a simple, the proportion of inequality in educational attainment in the population, which is accounted for by inequality among siblings. I didn't know these numbers, but and this is in different countries, and it's remarkably higher. It was 30-40% of inequality is accounted for inequality among siblings. Which brings me to this picture. This is the picture that motivated this thesis. And when he first showed me this several years ago, I told him, you have to study this. So here what he does. This is 9 different countries. It relates average attainment of educational attainment of children in a family, and it plots them against family size. So this is the average, and it goes down. And that's not particularly surprising. Poor families have more children. If you want, it goes back to the quantity-quality trade-off and so on. And it's true in many different countries. 2 children, 6 children, goes down, okay? Now, suppose that instead of the average, we plot the max. That's what you get. It's flat. It's completely flat as a pancake, which is an indication that what parents do within a family, it matters a lot. In his thesis, then looking at not all this data, but some of this data, he controls for birth order, fertility choices, and the like. If you take the max, it's still flat. And the reason why the mean goes down is because the mean goes through the floor. What this evidence tells me is that parental investment is important, but more important for what we saw today, both this paper and the previous one, is that when parents make choices on who to send to school, who to read books to, etc., they have lots of considerations in mind. They have resources, they have tastes, they have beliefs about the process of development, but they also have preferences about inequality within the family. And do I want to send all the children for 2 years to school, or do I send one kid for 6 years and the other 2 they stay home? And there might be gender considerations goes into play and all the like. So how this evidence square with what we learned today? I think we do need models of parental behavior and parental investment. We know that this is key for child development. Genetic variability in children and parents is bound to matter in fundamental ways, but I think especially if we want to influence policies and reduce inequality, maybe, we need to understand how the causal channels work through these different factors. And I think this paper, like the other papers we saw today, is the first step in the right direction, and this provides a number of very useful hints on where to go. And then I'll stop here.